Hello everyone. Now that we're familiar with how our eyes work, how light behaves, and some characteristics of light, let's start with some real life consequences. We are going to discuss about atmospheric refraction. Atmospheric refraction is the refraction of the light through the different layers of the atmosphere. This will be much easier to understand once we run through some real life examples. Assume there is a bonfire. If you stare at the fire, you will notice that the air above it acts odd. The air wavers above the fire. How is that possible? It is due to the atmospheric refraction. Let's understand this process step by step. The air above the fire becomes hotter than the air further up. This is obvious. The closer something is to fire, the hotter it will be. The hotter air is lighter than the cold air and has a lesser refractive index. Refractive index is a relative refractive effect of a medium on light. It means how much a medium can bend light with respect to another medium. In this case, the cold air and the hot air act like different media. The hot air has less refractive index than the cold air. The physical conditions of the refracting materials are not stationary. The refractive material in this case is air. The air above the fire will not remain at the same temperature. It will keep fluctuating due to the properties of the fire. The apparent position of the object, as seen through the hot air, fluctuates. Thus, the fire in the hot air also seems to be moving since the air itself is not constant. It will only remain consistent when the air will remain stationary. However, we've established that this does not happen. Fire is a small-scale example of atmospheric refraction. Let's move on to some large-scale ones. Here is a star. It is very far away from the Earth and seems to twinkle. Does it twinkle? Let's see. This boy on the earth may have gone stargazing. He should see the star this way, but can you guess what happens? His path of vision shows that the star is here. This occurs since the refractive index of the air keeps decreasing. This is a consequence of atmospheric refraction. Let's study this in detail. The starlight undergoes refraction before it reaches the earth. Each layer of the atmosphere is different and thus has a different refractive index. So the starlight constantly undergoes cycles of refraction as it moves from one atmospheric layer to the other. The atmosphere bends the starlight towards the normal. The result of the successive refractions is that the starlight is bent and the angle formed by the starlight with respect to the earth decreases. The star appears slightly higher than its actual position. With its angle change, the position of the star seems to have changed as well. The position of the star is not stationary since the atmosphere is not stationary. Like we saw in case of the fire, the air does not remain stationary. It fluctuates, and hence its refractive index also constantly undergoes a change. As a result of this, the position of the star changes. That's why stars seem to be moving. We also associate another thing with stars, twinkling. In fact, the twinkling of stars also has to do with atmospheric refraction. Stars twinkle because the path of the rays of light coming from the stars goes on varying. The atmosphere fluctuates, thus the ray of light also fluctuates in its medium. Some days stars seem to be very bright and the other day very dim. You may be wondering why planets don't twinkle. Planets receive their light from the sun and their light also undergoes the same kind of refraction as stars. However, planets are much closer to the Earth than the stars. If we try to calculate the refractive rays coming from all the planets onto the Earth, it will turn out to be zero. So, planets don't twinkle. Let's see another example of this. Here is the sun. Have you noticed that sometimes it comes too early and sometimes it leaves too late? I'm talking about advanced sunrise and delayed sunset. This is the actual path of the sunlight onto the earth during sunset. Here is the horizon from where the sunset is measured. However, due to atmospheric refraction, the sunset seems to be delayed. Similar to the way starlight experiences refraction, the sun also seems to be at a position higher than its actual position. So, advanced sunrise and delayed sunset is also because of atmospheric refraction. It is also why the sun disk looks flat during sunrise and sunset. The sun is a sphere, but during sunset and sunrise, it may look like a two-dimensional disk. This is also due to atmospheric refraction. Thank you, and I hope you've gained something from it.